In this video, we're going to be covering the Kubernetes architecture, and we'll finally start talking about the OpenShift architecture. So building on top of Docker and our container implementation is Kubernetes. And Kubernetes fills a very necessary task, wherein let's imagine now we have our architecture, we have our application, we've containerized it, it's running along. What happens if those containers fail? A really specific thing about containers is that they're extremely lightweight and they're intended to fail. And that's not actually a bug, but rather a feature. One of the problems with having VMs is that they're really heavy and they take long to start up, but they're also really safe. They're generally not going to fail. But when they do, it's a big problem. So how do we manage a system where it's very lightweight, the containers can fail anytime, they do, it happens. Well, what do we do to mitigate that? How do we create a system that's highly available, that's based on architecture that is intended to fail? And what that is Kubernetes. Kubernetes came in and said, okay, every time one of our containers goes down, we're just going to spin another one up and maintain the integrity of the cluster. Kubernetes is also going to take care of how do we orchestrate, how do we connect all of our containers so that we have an operating functional architecture. So, three of the things that Kubernetes takes care of: orchestration, scheduling, and isolation. Orchestration, that refers to how do we get those containers to talk to each other. So say we have a container over here that's running our front-end application. Let's say it's a store. And then over here we have another container that is our MySQL database. So one of the things we've talked about is that containers are meant to be a little transient, meaning things like their IP address is constantly changing. So how do we connect these two containers? What happens if the MySQL container goes down and we spin up another one? Well, now we have a container that has a completely different IP address. How do these connect to each other? Kubernetes resolves this issue with services. The other issue I talked about already is scheduling. So say we have 5 containers over here of MySQL, and 2 of them fail. Kubernetes can automatically build up a couple of more containers to just maintain that number 5. And we can also do interesting things like scaling them based on load. So say you start getting a lot of traffic to these containers, we can start bringing up more and more and more to support that load. Finally, we also have isolation. How do we make sure that if we're running a system with 7,000, 8,000 containers, that a failure of a couple containers is not going to affect any of the other containers that are running on that host machine or that are running on any other machine? So Kubernetes will help maintain the integrity of the system by preventing a failure on one container to affect the failure of, or to affect another container. So I'll talk just briefly about the Kubernetes architecture. And Kubernetes cluster, it's a set of node servers that run containers, and they're managed by a master server. So we have one master server that will be running all of our commands, just kind of similar to like Docker run, except we use a different command. It's called kubectl. And we use that to make changes and to spin up containers on nodes. So we'll have multiple nodes, and each node will be running multiple containers. So just then I was mentioning containers, but where Docker uses containers as the working object, Kubernetes actually uses what are called pods. And pods are one or more containers that are meant to share an IP address. So usually you keep a bunch of related containers. So say you have a couple of different front-end containers that you want to share the same resources. Although in all the demonstrations I'll be doing, we'll be sticking with just one container, one pod, which is a pretty common model. However, it is possible to run multiple containers within a single pod. I mentioned services briefly before, and services are what Kubernetes does to persist the IP address of our different pods. So again, we're not working with containers as much anymore as we are with pods now. So using services enables us to have a persistent IP address so that the pods can communicate with each other. Replication controllers are objects that are used in order to help scale out the application. We can use a replication controller to say, hey, you know what, we need some extra containers. We need some extra MySQL containers to handle all of this traffic load. A replication controller will ensure that we always have a minimum number that you set of pods. Persistent volumes and persistent volume claims are used for us to persist data despite any sort of container failures, or if we just bring the containers down. Essentially, we want to figure out a way to how do we maintain our data if we are going to be creating and bringing down all of these database containers. So we can use a persistent volume to maintain persistence even if our containers go down. And a persistent volume claim is just an object that we use to say, I would like to have access to this data, and we can use that to have multiple containers on different hosts all sharing the same persistent volume. So this is a great architecture if you wanted to create a containerized backend, or something like that for your databases. So now we've talked about Kubernetes, and we'll get into some diagrams and you'll see how this all fits together. We'll talk about OpenShift. And what OpenShift does is it takes Docker, it takes Kubernetes, and builds on top of it it packages it all together in this layer that is both user-friendly, it's great for system administrators, it's great for developers, and it provides a lot of these features that will also help you do things like create a continuous integration and continuous deployment pipeline. So some of the primary features that we'll be demonstrating both in this course and that are just excellent features that OpenShift provides on top of Kubernetes are the web console. So in the web console, you'll be able to orchestrate and manage all of your container cluster. You'll be able to do things like scale out your pods very easily. You can also manage some role-based access. So you can say, I would like this team to be able to access this application, this team to access this application, and you can kind of prevent teams from interfering with applications they're not supposed to. You can use a feature called source-to-image automation, and we'll be doing a demonstration on this later. But essentially what that is I can just point OpenShift to a Git repository where I'm running, I have my Java application source code, and OpenShift is smart enough to say, this is a Java application, and it'll look at all of the dependencies I need and build me a container and just start running it immediately. And it'll have all the dependencies that I need to run that application. OpenShift can run on your choice of cloud infrastructure. It can be hosted on-premise, like we have in this demonstration. You can run it in a private cloud, or you can run it in a public cloud, such as OpenShift Online. OpenShift routes are a specific resource just to OpenShift that build on top of Kubernetes, and that allows you to expose those services. So I talked earlier about how services are something that we can create persistent IP addresses so that pods can talk to each other. So how do you manage to take those IP addresses and then expose them to the world? Well, it's really simple. With OpenShift, you run one single command, and now your IP address is externally available. So let's take a look at this diagram here. We don't need to get into the weeds too much with it, but I think it's helpful to sort of see the master and how it interacts with the nodes. So as I mentioned before, you can see on the node we're running multiple pods, and you don't have to run two. You can just run one pod. And within this pod, we have, it looks like about 2 containers. There's one with our MongoDB. We have one with Apache server running on it. And these nodes, just because these pods are on the same node doesn't mean it's necessarily, they don't share an IP address or anything. The IP address is all shared within the pod itself. So say we wanted to have this Apache pod over here, this container that's running the Apache pod, be able to talk to this MongoDB. What we would do is we would create a service object for each of these pods, and that would allow us to consistently interact with each other. So as I mentioned before, here's our service layer. So OpenShift can be running on a physical, virtual, private, public cloud, any way that you want to, that's right for your organization. And we have our persistent storage over here. So our MongoDB should be able to access this persistent storage and maintain our database integrity. There's a couple of resources that are specific to OpenShift that I'd like to cover. So the first is deployment configurations. So this represents a set of pods created from the same container image, and this will help you manage things such as like doing rolling updates. It'll also help you out if you need to make any changes to your base image. It'll help you just deploy that. So it's part of the continuous delivery aspect of the continuous integration and continuous delivery pipeline. And build configurations are great. So let's say we have any changes to an image that we're using. So let's say MySQL releases a security patch or something for their base image. We can configure OpenShift to where it will automatically build out a new version of our containers so that we can make sure that our security patches get through the quickest time. And as I mentioned before, routes are also specific to OpenShift. So I'd like to take a second to take a look at the technology stack that's used by OpenShift. So in this diagram, the items that are highlighted here, this is the parts of OpenShift, and then the parts in gray are not part of OpenShift, but they're what OpenShift is built on top of. So of course we have our RHEL, Container Optimized Operating System, and on top of that we have Docker, which is our container implementation that we've already talked about, and we have Kubernetes, which is responsible for orchestrating the containers. And we have etcd, and etcd is what Kubernetes is. It's a distributed key value store, so it's what Kubernetes uses to store a lot of their information and resources, any configuration, things like that. So now we're going to get into some of the OpenShift and how it interacts with these things. So OpenShift Kubernetes extensions, this is just some simple additional resources and configurations, so things like routes, specific only to OpenShift, and these are actually also stored in etcd. So really you can think of these as like being on top of each other, right? These are just extensions to etcd. We have some containerized services, so I mentioned that a lot of OpenShift actually runs in containers itself, and these services such as authorization, networking, the image registry, these are all running as pods in the background, and they're all containerized, and you can scale them just like you would anything else. We also have some runtimes and XPaths images. So this is for some of the source to image stuff that we'll get into later. But OpenShift comes already with all of these images and these runtimes attached. So you don't need to go necessarily hunting around Docker Hub in order to find your Java image or your Ruby image. These are already baked in, and they're well maintained by Red Hat. And finally, on top of that, we have our web console, our CLI, and we've talked a bit about that, and I'll get a little more into some of the CLI commands. It's also built on a REST API, so you can feel free to make your own integrations. You can use IDEs to integrate more easily with Red Hat OpenShift.